One of the reasons that we conduct multiple regression is to better understand which variables contribute to variation in the response variable. We would like to know which variables are most important in terms of explaining that variation. So we do things like partial squares and semi-partial squares to look at the contribution of a single variable to the model as a whole. We want to explore individual variables in the context of a model in multiple logistic regression as well. And we're going to look in this video at two tools that we can use to do that. One is the incremental g-squared. You can think of the g-squared as a sort of r-squared. It is the difference between the residual deviance of models, and it's used for variable selection in model building. You know in regular linear regression that if a model ends up leaving a lot of residual, it's not as good a model as if a model just leaves a little residual. Well, the same thing here. If a model leaves a lot of residual deviance, that's the analog to residual in multiple regression, it's not as good a model as if it leaves a little bit of residual deviance. And by removing a variable and seeing how much the residual deviance changes, we can know whether or not that variable was important in our model. The second tool that we can use is the Akaike Information Criterion, or the AIC. Remember that we seek parsimony in our model building. The AIC looks at both how much g-squared changes as well as how many variables are in our model. If g-squared changes a lot when we remove a variable, that means that variable's important. But it gains in importance if we have few variables in our model. So it helps us play that balancing act between adding variables but trying to keep a parsimonious model. Smaller values of AIC indicate a better model. Now, of course, we're only getting an overview of logistic regression, so there's a whole lot more that we could do in terms of incremental g-squared and AIC, but I want to show you a couple examples just to give a flavor. Let's take a look at two additional models. We already looked at a model in which we had both SES and perception. Let's create model 2 here as just SES. So I'm going to look at just SES in the model without perception, and then get a summary. And I'm going to look at the difference in the deviance of the GML with the full model and the reduced model. Now, if you think about what this deviance is going to tell us about, it's going to tell us about perception, not SES. Why? Because SES is in the full model, and it's also in model 2 that we just created. So the change in the model is perception, and so the change in deviance will be due to dropping perception from the model. What I find is a change in g-squared of 139.9. How to interpret 139.9? If you were in my nonparametrics class, in which we talked about the distribution of the g-squared, which it turns out is associated with a chi-square, we could learn more specifically how to interpret this. Right now, we're just going to look at some relative comparisons to the drop in g-squared. I will tell you that this is a lot. If I were to look at it compared to a chi-squared distribution with the appropriate degrees of freedom, we would find out that this is a big change in g-squared. But rather than focusing on that, let's just compare it to what happens when we drop SES instead of perception. So here I'm creating model 3, and in model 3, I'm going to look at the change when I take out SES. I can get a summary for the model. I can see that perception still appears to be an important variable, even in this one variable model. But now let's see what happened when we changed from the full model with both SES and perception, and then the model in which we just dropped SES, 3.81. Note the difference. Up here, 139.87 when we dropped perception from the model, 3.81 when we dropped SES for the model. So it's not nearly as big of a drop when we drop SES, meaning SES is not as important in our model. That really matches quite nicely with what we saw here when we looked at the full model of the p-values, noting that both of these had low p-values, but for perception, it was a really, really tiny p-value. So if I had to just have one model with one variable, I would certainly choose perception over SES. But what about if I had a choice of a model with both perception and SES, or just perception? We've looked at the change in G-squared. Now let's look at the change in the Ikeki information criterion. Remember that we want small values. Remember also that this will be looking at two things at once. What's the G-squared look like, and how many variables are in the model? So first we're going to do the full model to give us a baseline to compare to, and that's 642. Now I'm going to look at the model with just SES. So with just SES, the Ikeki information criterion is looking at how much the G-squared changed, but also looking at the fact we only have one variable. It will like that we have one variable, but it won't like it if G-squared changes a lot. And it changed a lot. The Ikeki information criterion went up, even though we dropped a variable, which gives us more parsimony. We had quite an increase in the AIC. By comparison, when we look at the model with just perception in it, we had hardly any change at all in the Ikeki information criterion. So now we have a one variable model, which the AIC likes, and the G-squared didn't change too much, which the AIC also likes. The full model had the lowest AIC, but the fact that it doesn't change much when comparing it to just perception means that perhaps I will include SES if indeed I can measure it very cheaply. Perhaps it's already available to me. But otherwise, I probably am just going to want to stick with perception. If I don't have SES readily available and there's some cost in collecting that data, it's probably not going to be worth it. So what I have given you is a flavor for logistic regression, both simple logistic regression and, more importantly, multiple logistic regression. I hope you see the parallels. We can use it to build models in which we predict a categorical response. We can use it to compare different models to see which variables appear to be explaining or predicting better for our categorical response. This comparison is based upon a change in residual deviance, just like it's based on a change in residuals when we do regular multiple regression. And there are additional parallels that I'm not going to get into because I just want you to see that there is a way of doing regression when we have a categorical response variable. I want you to understand something about it when you come upon it when you're reading the research literature, and I want you to know that with further training, when you have these sorts of situations in your own research, you can learn more about it and actually use this as a statistical tool, adding it to your toolbox that has gotten quite a bit larger this semester. You should be proud of what you have. I sure hope you're proud of what you have, because that's as far as we're going for this semester. There are additional classes that are available if you're interested in learning about different situations and learning more about these tools, and I hope to see some of you in those classes. But even if not, you've got a good base for starting to work on developing your own research projects.